This is a short tutorial on weak acids. Before we start talking about weak acids, we must remind ourselves what the difference between strong and weak acids is. Strong and weak do not refer to concentrated and dilute. However, strong and weak refer to whether or not the acid-base reaction goes to completion or is in equilibrium. Strong acids like hydrochloric acid, when placed in water, completely dissociate into hydronium ion and chloride ion. Conversely, weak acids, when put in water, only partially dissociate and set up an equilibrium between the acid and the conjugate base. If we take a look at the example here, which is acetic acid, normally found in the kitchen in the form of vinegar, if we place acetic acid in water, in fact, about 95% of the acetic acid remains undissociated, and only about 5% actually reacts with water to give hydronium ion and acetate ion. Many biologically important molecules are either weak acids or weak bases. Amino acids, for instance, contain both a weak acid, a carboxylic acid, and a weak base, which is an ammonia base. Fatty acids are used either to form structures like cell membranes or also are nutritionally important. Ascorbic acid is vitamin C, and aspirin, which you find in your medicine cabinet, at the core is a molecule called salicylic acid. Well, to discuss weak acids and strong acids, we first need to talk about acid strength. We do that using a constant called the acid dissociation constant, Ka. And being able to calculate Ka for weak acids is very important. So the acid dissociation constant is just a special statement of the equilibrium constant, specifically for an acid-base equilibrium. If we have some generic acid HA and we place that in water, we'll set up an equilibrium between HA and water and hydronium ion in the conjugate base for HA, which would be A-. We can treat this acid-base equilibria just like any other equilibrium and write an equilibrium constant equation, which is going to be the amount of product that we've produced over the amount of reactant. If we go ahead and substitute in the acid-base reaction shown above, we see that Kc equals the hydronium ion concentration times the conjugate base concentration divided by the undissociated weak acid HA and water. So this would be the standard equilibrium equation, but specifically for acid-base reactions, we often write a Ka expression which looks like this. Because we are working in water as a solvent, the concentration of water will be a constant. If we pull that over on the left-hand side of the equal side with our equilibrium constant, we now have a Ka, which is defined as the equilibrium constant times the concentration of water, which equals hydronium ion concentration times conjugate base divided by the undissociated weak acid. Ka is a measure of how strong an acid is. Weak acids typically have a Ka of less than 1. Undissociated acid in the denominator is bigger than the numerator, giving us a Ka less than 1. Well, here's a chart of Ka strength for common acids. Of course, we're measuring these in aqueous solutions. If we decided to use a non-aqueous solvent, we would have an entirely different set of equilibrium constants. The larger the Ka is, the stronger the acid. And typically, what we define as strong acids are the ones that are shown in the red box. Everything with a Ka less than what we show in the box typically is defined as a weak acid. You'll notice that the second proton coming off sulfuric acid is in fact a weak acid proton as opposed to the strong acid proton which we have up in the box when we're losing that first hydrogen ion. We see carbonic acid, which is formed by the dissolution of carbon dioxide gas in water. is about 4.5 times 10 to the minus 7th, very near neutral pH. And in most natural water systems, it's this dissociation which controls the pH. Of course, carbonic acid is diprotic. The second hydrogen comes off carbonic acid at about 4 orders of magnitude smaller Ka. And then finally, we have the water dissociation constant as opposed to the hydronium ion dissociation constant at 1.8 times 10 to the minus 16. Factors that affect acid strength include the polarity of the hydrogen bonded to whatever the central atom is for these acids. So if we take a look at a chart and take a look at the difference between electronegativity between the hydrogen and whatever it's bonded to, translate that into the partial positive charge on the hydrogen in that molecule, and then take a look at the corresponding Kas, what we see is as the electronegativity difference becomes smaller and smaller, it becomes more and more difficult to pull a hydrogen off as H+, which means that our Ka becomes smaller and smaller and smaller. Ka also depends on the size of the central atom. Typically, the larger the central atom, the more acidic the hydrogen ion is. It depends on the overall charge on the acid that we'll see in a couple of slides. And also the number and type of atoms bonded to whatever our central atom is. Many of the acids that we will encounter are polyprotic acids, meaning that they have more than one acidic proton to lose in acid-base reactions. For polyprotic acids, each successive hydrogen ion is harder to get off, requires more energy, which means we have a smaller corresponding Ka. The increasing negative charge on the base molecule holds the next hydrogen ion tighter, which means that it will have a lower pKa. That means that it's less acidic. Well, what law do we know that governs the attraction of positive and negative charges? Well, that would be Coulomb's law, shown here, as we've looked at many times before. As the base molecule continues to lose hydrogen ions H+, the base molecule continually becomes more negatively charged. One of these Q's goes up. That means the attraction for the next hydrogen ion that wants to leave is going to be higher. The force holding that hydrogen ion will be higher, and it will result in a less acidic, more tightly held, smaller Ka proton. Well, let's take a look at the example sulfuric acid, which is diprotic. The first hydrogen ion coming off sulfuric acid, it comes off so easily that the Ka is about 1,000, and we have a strong acid. But once we have released that first hydrogen ion, now we have a negatively charged molecule called bisulfate. The second hydrogen ion coming off bisulfate has a much smaller Ka, and that second hydrogen ion actually is classified as a weak acid. If we take a look at a triprotic acid like phosphoric acid, you can see that every time we lose a hydrogen ion and the base molecule ends up with an additional negative charge, the next hydrogen ion off becomes harder and harder to remove from the molecule. So we have 10 to the minus 3, and then a 5 order of magnitude difference 10 to the minus 8th, and then another 5 order of magnitude difference 10 to the minus 13th as we lose successive hydrogen ions. We already talked about carbonic acid. The first hydrogen ion coming off carbonic acid is right around pH 7, which means that carbonic acid is one of the molecules that controls natural water pHs, which are typically slightly below 7. But that second hydrogen ion, 4 orders of magnitude harder to remove from the corresponding molecule. Finally, we have hydronium ion with a Ka of 55, a strong acid, losing a hydrogen ion, becoming a water molecule. Removing the next hydrogen ion, however, to form hydroxide gives us a Ka of 10 to the minus 16th, a much more energetic, difficult proton to remove. Whenever we have weak acids involved in acid-base reactions, we can determine the position of the acid-base equilibrium based on the Ka values. If we take a look at two weak acids, ammonium, NH4+, and diprotic phosphoric acid, H2PO4 1, we see from the Ka values that these are both very weak acids. But regardless of how weak these acids are, one of the acids will be stronger than the other. So based on the Ka values, can you tell me which of these two acids will be stronger? Well, if we look at the Ka values, we can see that 10 to the minus 8th is a larger number than 10 to the minus 10th, and diprotic phosphoric acid, in fact, is the stronger acid of the two. Well, if these weak acid conjugate base pairs are involved in an acid-base reaction, which direction will the equilibrium lie, towards reactants or towards products? Well, the first thing that we need to recognize is that each side of the balanced chemical equation has both an acid and a base. On the left-hand side, we have ammonium as our acid and monoprotic phosphoric acid as our base. We know that ammonium is the acid going from left to right because it loses a hydrogen ion. We know that monoprotic phosphoric acid is the base because going from left to right it gains a hydrogen ion. On the right hand side we have ammonia, NH3, as our base and diprotic phosphoric acid as our acid. Again, if we look at the equation going right to left, we see that diprotic phosphoric acid loses a hydrogen ion. That's the definition of an acid. We see that ammonia gains a hydrogen ion. That's the definition of a base. When we have an acid-base reaction like this with acid-base pairs, one side of the equilibrium will always have the strongest acid and the strongest base. The other side will always have the weakest acid and the weakest base. Well, we have already identified diprotic phosphoric acid is the strongest acid in this acid-base equilibrium. That means that ammonium, NH4+, is the weakest acid. We know from our discussions of thermodynamics in the universe that reactions always move from strong reactive unstable molecules to weak unreactive stable molecules, and the difference in energy is liberated to the external surroundings. That means that this equilibrium will shift from the strongest acid base to the weakest acid base, meaning that this equilibrium will lie to the left. We know which direction the universe favors because we know that the universe will always take reactive molecules and try to form more stable unreactive molecules. In this case, the equilibrium constant Kc for this acid-base reaction will lie to the left, meaning we have more reactants than products. Kc will be less than 1. Finally, let's talk about the relationship between Ka and pH. Strong acids completely dissolve in aqueous solution to form hydronium ion in the corresponding conjugate base, in this case chloride. The initial concentration of HCl equals the final concentration of hydronium ion, and since we know pH is the negative base 10 log of the hydronium ion concentration, we can easily calculate the pH just by substituting in the initial concentration of HCl that we put into the system. Weak acids are entirely different. Again, if we take a look at a weak acid like acetic acid, we know that this is set up as an equilibrium. It's not a completion reaction. And we know from the previous slide that about 95% of the acetic acid remains undissociated in solution. Well, we can go ahead and write our Ka for this reaction. And if we are trying to figure out pH, we would want to isolate hydronium ion on one side of the equation. So let's rearrange the algebra. And now we see that the hydronium ion concentration is equal to the Ka times the undissociated weak acid concentration divided by the conjugate base concentration. Well, if we're trying to find pH from this equation, we know that pH is the negative base 10 log of the hydronium ion concentration. So if I take the negative base 10 log of both sides of this chemical equation, what I end up with is the pH is equal to the negative base 10 log of the hydronium ion concentration, which is in turn equal to the negative base 10 log of the Ka times the ratio of undissociated acid divided by the conjugate base. Well, I can further play with this equation, now taking advantage of the fact my definition for P is the negative base 10 log of anything, and now my pH, negative base 10 log of the hydronium ion concentration, is equal to my pKa, negative base 10 log of the Ka, minus the negative base 10 log of the ratio of the undissociated acid to the conjugate base. Well, what you should notice here is that my pH does not depend on the concentration of acid. It depends on the concentration of acid divided by the concentration of conjugate base. It depends on the ratio of those two concentrations. Well, the equation that we've just done the algebra for is referred to as the Henderson-Hasselbalch equation, and it is used in the laboratory constantly to calculate concentrations for materials like buffers, which will be covered in a separate presentation.